Hello again, Mr. LaBeouf, and I've posed two queries here for 7th and 8th graders. If x is greater than 0, explain how, number 1, x and x times the square root of 2, and x times the square root of 3, and 2x can form the sides of a right triangle. And if you see these questions and wonder, is the Pythagorean theorem involved? You're right, it is. I suggest that you pause the video and see if you can answer these two questions. Give it a try. I'm going to do the same thing and come back. Nice to see you again. Here's a diagram of a right triangle where I've labeled the two legs A and B and the hypotenuse C as is standard. And the Pythagorean theorem says that if you have such a right triangle, the square built on side A, its area plus the area of the square built on side B will be exactly equal to the area of the square built on side C. Algebraically, the area of the square down here would be A squared, the square built over here would be B squared, and the square built on the hypotenuse is C squared. So the very familiar A squared plus B squared equals C squared. The two questions that I posed, however, actually involve the converse of the Pythagorean theorem. There are hundreds of proofs of the Pythagorean theorem. Many of them are very similar. There's also at least one proof of the converse of the Pythagorean theorem. A converse of a statement means that you can go in the other direction. So in other words, if you have three positive quantities A, B, and C, and if it is true that A squared plus B squared equals C squared, then those three lengths can form a right triangle. That's the converse of the Pythagorean theorem. Since the converse is also true, we can put a double arrow here. It can go in both directions. So the first question involved these quantities, x, and x times the square root of 2. And I wasn't trying to be tricky when posing these questions. The quantity on the far right here, the last one, is the biggest one. It's C. So we can take these three quantities, plug them into the Pythagorean theorem formula, and get x squared plus x squared. In this case, A and B are the same quantities. They're both x. And will that be equal to x times the square root of 2 squared? And on the left side, of course, x squared plus x squared is 2x squared. And on the right side, when you square x times the square root of 2, x times the square root of 2 times x times the square root of 2. These two numbers, of course, the square root of 2 times the square root of 2 is by definition 2. So on the right side, we have 2 times x, or 2x squared. So that answers the first question. The second question involved these three quantities, x times the square root of 3, and 2x. And once again, the third quantity is C. That's the biggest quantity. And of course, x has to be positive here because we're talking about geometric lengths. And if 2x is greater than x, obviously, 2x is also greater than the square root of 3 times x because the square root of 3 is approximately 1.732. That was easy for me to remember as a youth. One of the niceties of math. Beautiful. There's a lot of talk about cross-curriculum learning nowadays. So let me make my contribution. Our first president, George Washington, was born in 1732, and coincidentally, the square root of 3 is approximately 1.732, and 2x is greater than that quantity. So once again, we'll square the x, and we'll add that to the square of x times the square root of 3, and then we will square the 2x and see if it works out. On the left side, we have x squared plus. Now, when you multiply this quantity by itself, x times the square root of 3 times x times the square root of 3. The square root of 3 times the square root of 3 is 3. By definition, x times x is x squared, so we have 3x squared on the left side. On the right side, we have 2x times 2x, which is 4x squared, and x squared plus 3x squared is also 4x squared. So we've proven the second case. This lesson, like many that math teachers will devise, has a couple of different objectives. The first objective for 8th graders, certainly, whether they're taking Algebra 1 or a non-Algebra 1 course, familiarize the students with the Pythagorean theorem and also a little basic algebra, the squaring and the adding of like terms that we did previously is excellent practice, reinforcement for 7th and 8th graders. But the ulterior motive is that this exercise introduces students to a topic that comes up in high school, in geometry, also at the beginning of trigonometry with the right triangle trigonometry. This introduces students to what are called two special triangles. And I happen to have two tools, some plastic triangles that are sold widely because these triangles are dealt with in high school math, these two special triangles. The first one is what we can call an isosceles right triangle. So let me construct the isosceles right triangle. The isosceles right triangle is also known as the 45-45-90 right triangle. And one of the basic Euclidean truths is that when you have an isosceles triangle, and we'll indicate that those two sides are the same length, there's a proof that's in Euclid's Elements that states that the angles across from those congruent sides will also be congruent. And since all right triangles have a total of 180 degrees, and we have 90 degrees here, these two must be 45 degrees each. And the converse of this Euclidean theorem is also true. If you have a triangle that has two 45-degree angles, and the other angle must therefore be 90, then the sides across from those congruent angles are also congruent. It works in both directions. Now, since these two sides are the same length, we can call each one of them x. And applying the Pythagorean theorem, we'll call the hypotenuse c. And applying the Pythagorean theorem to this triangle, where each of the x's is a and b, we get x squared plus x squared equals c squared. X squared plus x squared is 2x squared equals c squared. If c squared is a quantity, then c is the square root of that quantity. So c is equal to the square root of 2x squared. In a previous video, I talked about how we can simplify roots, that the square root of a product is equal to the product of the square roots. So this quantity here can be thought of as the square root of 2 times the square root of x squared. The square root of x squared, by definition, is x. And so we have x times the square root of 2. That is the value of c. And so that this is what was going on in my first question. I was really having the students discover and deal with the isosceles right triangle or the 45-45-90 right triangle, and coming to the realization that the two legs are x and the hypotenuse is x times the square root of 2. Now, one last little connection about this one before we move on to the second question. This triangle can be thought of as half of a square, and this hypotenuse, c, would be the diagonal of that square. And in another video, we dealt with that. The video about, I think I designated it for 7th grade, the video about the distance from home plate to second base on a baseball field. When you have any square, the length of the diagonal is the square root of 2 times the length of one side of the square, and this is just half of that square. So it's the same situation. And with my other plastic triangle, I've just constructed the other so-called special right triangle of high school math, and that is the right triangle that has angles of 30 degrees and 60 degrees. And for a long time, I kind of struggled with the why of this one until I came up with an easy answer to the why. But the rule is this, that with a 30, 60, 90 right triangle, the hypotenuse is twice the length of the shorter side. So if we call the shorter side over here, the one across from the 30-degree angle, if we call that x, then this rule tells us that the hypotenuse is twice that length. And I'm going to come back to that in a moment. That's the thing that I had to work out for myself. But it's a relatively easy matter to, if you accept this, to figure out the value of this leg over here. Let's call it B, with the x here being the other leg A, and the 2x, the hypotenuse, is the C. So we would get this. X squared plus B squared equals 2x squared. And we'll solve for B. Now, this is one of those Pythagorean theorem problems that is slightly harder than trying to find the hypotenuse. If you have the two legs of a right triangle and you plug their values in for A and B, you can easily get to C. This is only slightly harder. It involves one more step. Literally just subtracting something from both sides is the only difference between this and an easier Pythagorean theorem problem for 7th graders. The B squared here is going to be B squared equal to 2x squared, 2x in parentheses squared, minus the x squared. I'm trying to isolate that B, so I subtracted x squared from each side. B squared equals, when you square 2x, 2x times 2x is going to be 4x squared. So we have 4x squared minus x squared. 4x squared minus x squared is 3x squared. So B squared equals 3x squared, and therefore B would be the square root of 3x squared. B is equal to the square root of 3x squared. And like we did a moment ago, we can simplify this to the square root of 3 times the square root of x squared. The square root of x squared is x, so B is equal to x times the square root of 3. And this is the second question that I posed at the beginning. If you have three quantities where x is positive, if you have x times the square root of 3, and 2x, you can form a right triangle with those three quantities. And in fact, the right triangle is this special one, the 30, 60, 90 right triangle. And to finish up this video, I want to share with you how I came to more fully understand and buy into this 30, 60, 90 right triangle. This notion of why is it that the hypotenuse is twice the length of the shorter leg, the short leg. And what I realized is that this 30, 60, 90 right triangle can be thought of as half of an equilateral triangle. Now, similar to with the isosceles right triangle, earlier in the video we talked about how when you have an isosceles triangle and you have so you have the two equally length sides, the angles opposite those equally length sides will also be congruent. With an equilateral triangle, all three sides are the same length, So the angles across from them, in a similar way, have to all be the same degree measure. And since every triangle has a total of 180 degrees, with an equilateral triangle, we have 360-degree angles. So this over here is 60 degrees. And then up here, you've got a 30-degree, and then also a 30-degree angle over here. So you have a big equilateral triangle. All three of those sides are the same length. And if you choose to call one of the sides 2x, this one over here would be 2x as well. Down here, that would be 2x. And the altitude that's dropped from this vertex down to the base divides the base into two equally sized pieces. So they're each x, adding up to the 2x. So this is an explanation of why the 30, 60, 90 right triangle has a hypotenuse that is twice the length of the shorter leg. And then the Pythagorean theorem tells us that that other leg, which happens to be the altitude or the height of the equilateral triangle, is the square root of 3 times x. Two special right triangles. So long.